Welcome to clickmyproject.com. Yeah, now let us discuss about the low complexity modem designed for GFDM. Yeah, now let us discuss about the abstract of the process. So here we are using the GFDM, that is a general of frequency division multiple access. So in this project we propose a novel modem structure for GFDM by taking advantage for the particular structure in the modulation matrix. So in our proposed method, transmitter is based on modulation matrix. So through application of FFT, so that is a fast Fourier transform, to reduce the implementation of complexity. So ununified demodulated structure for matched filter, so that is MF, and then zero forcing, that is ZF, and then minimum mean square error, so that is MMSE. So receivers is also in the process to derive. So the proposed demodulation technique harness the special block, that is a circulation property of the matrices. So in this involved in the demodulation stage to reduce the computational cost of the system implementation. So here we derive the closed forms of the ZF, so that is a zero forcing, and MMS is the receive filters. So additionally, in our algorithm do not incur any performance loss as they maintain the optimal performance. So the computational cost of our products techniques analysis in detail or compared with the existing solution, so that is an existing problem of to recover choosing the proposed method that are known to have the low complexity of the process. So it is shown that through application of our structures a substantial amount of computational complexity reduction can be achieved. So the simulation process is done by using the MATLAB of the process. Yeah, now let us discuss about the flow diagram of the process. So first of all, generate the input data, so randomly generated. So this is the transmission model, channel, and then receiver model. So in the transmitter model, generate the input data, that is like a randomly generated, and then conventional encoding the data to encode the process, to encode the input data as the convolutional by using the convolutional encoding, and then that is a serial to parallel conversion. So in case one input get to the many output, so that is a serial to parallel conversion, and then by using the interleaving coded data to interleave the coded data by using the serial to parallel conversion. So our output is getting the input to the interleaving coded data of the process, and then binary to decimal conversion, so that is a BCD. So the BCD process, the values of values should be in the binary number, that should be converted into the decimal. So that is a process of binary to decimal conversion. And then here we are using the QA modulation, so that is a quadrature amplitude modulation, and then pilot carrier insertion. So by using the pilot carrier insertion, it should be efficient compared to the process of particular low property. And then here using the IFFT process, so that is the inverse fast Fourier transform. So in the inverse fast Fourier transform is important to getting the fast Fourier transform reverse operation of the inverse Fourier transform, and then adding zero padding. So zero padding is a ZP, that is to adding the zero padding of the process by using the values to technique, the adding zero padding technique of the process. So whatever it may be, it calculating the adding the zero padding of the results. And then channel, so in this channel the relay channel fading is used. So in the relay channel fading by using the AWGN, so that is a additive white Gaussian noise process. So here we are using the relay fading channel. So the relay channel channel compared to the Gaussian fading channel, it should be efficient also, and the channel should be very clarity to given the efficient, and accuracy should be high. So the reservoir model technique, here we are removing the zero padding technique, so all the process is inverse to the transmission model of the technique. So here we are using the ZP by removing the ZP of the process, and then adding the zero forcing equalizer, so that is a ZF equalizer for adding the process, and then it should be FFT. So in the fast Fourier transform, so in transmission model here using the IFFT process, in the receiver model here using the FFT process. So whatever it may be, the pilot removing it should be done. So here using the QAM demodulation technique, and then decimal it should be converted into a binary value of the process, and then de-interleaving the data. So here we using the interleaving coded data, that is a process of for the entering the process of the particular process, and then de-interleaving data, it should be de-interleave of the particular process, and then finally the decoding the values by using the Readme algorithm. So by using the Readme algorithm, that should be decoding the data, finally calculating the bit error rate and signal error ratio of the particular process. So these are the overall flow diagram of the process. Yeah, now let us discuss about the running procedure for the process. So click the main file and then run. So it has some time to running in the process. Yeah, now all the figures are displayed. So first of all, the input data. So in this input data, this is a randomly generated. So by using the process or randomly, here we are using the randomly generated of the process. So in the next figure, it's IF15 data. So IF15 data should be process of the process, inverse Fourier transform, and then zero parallel result. So zero parallel results means ZP of the process. So that is a zero parallel result. And then next figure, that is a cyclic preface. So that is a CP insertion of the process. And then so these are all the inbuilt functions. So noising by using the AWGN channel and also a Rayleigh fading channel. So the next figure, that is a zero forcing equalizer. By using the zero forcing equalizer, that is a ZF. So that is a concept of ZF. So the next figure, and then cyclic prefix removal. So CP removal by using the, this is also inbuilt function of the process. The next figure, that is a zero parallel removal. So whatever it may be in the transmission model, that should be removal in the receiver model. So similarly the same. So the F50 data, IF50 and then F50 data, and then pilot carrier add, and it should be in the removal. So again finally decoded data, encoded data, it should be same for the decoded data. So these are the transmission, channel, and then receive, and then the describing about the simulation result. So that is a ZF solution. That is a zero forcing equalizer design. So this is 64 QAM modulation. So this one is a proposed ZF. So zero forcing. So direct ZF is so EB by N naught is the noise, and BR is a bit error rate of the value. So it should be reduced 10 power minus 2. So the value should be calculating ZF solution 64 QAM modulation after technique. So proposed ZF is a zero forcing equalizer, and then BR is a bit error rate, and then EB by N naught of dB. So EB by N naught of dB. So whatever it may be, the value should be calculated. So in the next figure, Z4 equalization is 60 QAM modulation. So that is a 64 QAM modulation, and this is 16 QAM modulation. So this is a ZF solution. So the proposed ZF is calculating the black and blue. So the direct ZF and proposed is more or less same, and the direct MMSE is a minimum mean square error. So the EB by N naught of dB, and then BR it should be reduced. So the previous figure, it is a 64 QAM modulation. This is a 16 QAM modulation of the process. So these are the different type of process. And then the next figure, the MMSE solution of 64 QAM modulation. So this is a proposed ZF and general direct ZF by using the BER and EB by N naught of dB. So whatever it may be, the MMSE, the minimum mean square error calculation, and then solution 64 QAM modulation, it should be processed. So whatever it may be, the value should be the next figure, that is a complexity comparison bit. So in this figure, the computational complexity comparison of different GFDM. So that is a generalized frequency division multiplexing transmitter technique, and the OFDM transmitter technique is NS is equal to 1024. So already we've seen that NS is equal to 16 and NS is 64. Here we are using the NS is equal to 1024, and the block length is equal to 5 up to 30. So the proposed transmitter is, so the proposed transmitter, and then the proposed GFM transmitter. So here we are using the proposed GFDM transmitter and then OFDM transmitter. So by calculating complex multiplication, whatever it should be easy to use, and our proposed method is denoted by pink color. Yeah, in this next figure, computational complexity comparison of different GFDM receiver technique and the OFDM receiver technique. NS is equal to 1024. So the block length must be 0 to 20, and the number of complex multiplication is 10 power 0. Compared to all the in the previous figure, we are calculating the transmitter, and in this figure we are calculating the receiver of the process. So these are the transmitter and receiver of the particular process. So in the next figure, so in this next figure, so this is the next figure. So by calculating the block length, so the same process by using the number of complexity of multiplication. So computation complexity of different receiver and techniques of the OFDM receiver technique, NS is equal to 1024. The proposed receiver on proposed ZF receiver, and the value proposed MF receiver. So that is a ZF means a zero forcing equalizer, and MF means mean equalizer. So these are the important process. So these are the running procedure of the process. Thank you. Thank you for listening this video.